In a previous video we looked at discrete probability distributions, and we also mentioned there's this thing called continuous variable probability distributions, and that's what we're going to focus on in this video. So as you can see by the title, this is the basics about using continuous probability distributions, and in particular the most common type, the normal probability distribution. So it's, as was mentioned briefly in an earlier video, this is a type of continuous probability distribution. That is, the variable is a continuous variable. So the normal distribution is synonymous with the so-called bell-shaped curve, which is a common way of describing it in everyday language. So bell-shaped curve, or a bell curve, and its profile looks like an old bell. In this video, it's a bit of a how-to video, a little bit about the theory, but mainly it's about how to do it. And basically graphics calculators will be the engine behind our calculations, not tables and not other means. So we're going to use graphics calculators and the TI Nspire as well, and darn it, my software, just as I'm shooting this video, is not working because of a location of a certain file on the server that I'm working off. So I'm going to have to use a document camera to take a video of me punching in the keys, but it should still work fine. So apologies in advance if there's any minor focusing issues on it. Maybe one day I'll remake this video using my Navigator software so you can see it better, but this should be okay. By the way, I'm using a non-CAS TI. I'll explain how a CAS might have some different features or extra features as we go. Also in this video we'll be transitioning from what we've seen previously, probability distributions, to what we call probability density functions, or PDF as you might see it on the calculator or in tables. And you can see in that diagram 1. So that's an example of a sketch of a probability density function. We'll get on to that in a minute. But prior to that we saw probability distributions where we would have the probability measured on this axis and the various categories or scores measured on that axis there. But with the probability density function, we're looking at, now you can see, oh, there's no scale. Well, there is an implied vertical scale there. Because this goes to negative infinity, it's problematic to draw it in, but we would have a scale there. And so probability would go on the scale. Along here, we don't have x. Okay, we have what's called the normal variable. This one's called the standard normal variable. So we have a normal variable along there. Basically, it talks about the deviation, whether it's normal variable or standard normal. If it's normal, by the way, it'll be an x. If it's standard normal, it'll be a z. It's talking more or less about the deviation above or below the mean. So we have different things measured on the axes. Okay. When we say the normal distribution, well, there's actually many normal distributions. We can change things like the mean and the standard deviation. So there are many types of normal distributions. There's one particular key one called the standard normal distribution. That's an important one for this video, and it's just an important one full stop. So standard normal distribution, and that's the one that uses that symbol Z that I just spoke of. So that's denoted as Z, and that's what we're going to focus on mainly in this video. In further videos we'll be referring to X, which is a different type of normal distribution, and I've just seen that I've written the word distance there. How weird. Okay. So let me put in distribution. Sorry about that. Okay, so there's many normal distributions, and we're looking at the standard one in this one, which is a good place to start, but we will look at other ones in the next video. Now we'll have the variable x. Now I mentioned briefly, and I didn't write it down, standard normal distribution has a particular setting for the mean being mu. The mean is 0, and as you saw on that diagram there, you saw that the center point there was 0. So that's a deviation of 0 from the mean. Okay, and the mean is set at 0 there for that one, and the standard deviation is 1. So that's what makes the standard normal distribution. Alright, when mu equals 0, the mean equals 0, and sigma, the standard deviation, equals 1. So that's very important. Now the forms you'll see all of these tasks in are like this. If we have the probability that x is between a and b, we basically will have two values there and x in the middle. If it's a standard normal one, it'll be the same, except for it'll have z in the middle, and that'll pertain to this video. Okay, so you'll see ones with z in this video and x in the next video. Now they're both the same as these two corresponding ones here. Notice how a is less than or equal to x, which is less than or equal to b, is the same as when it comes to probability as a is less than x, which is less than b. So this has a correspondingly to z has the same outcome there. The reason why is that when we have the area under a curve, now think integration here. Okay, think your calculus and your integration that you've done. Basically the area under a curve in this situation is the same as that situation. Okay, so they produce the same area, so they are one and the same. So it doesn't matter whether we're using inequalities less than or equal to or less than. Okay, and the same applies for greater than or equal to and greater than. Okay, so it's one and the same because it makes no difference to the area under a curve, because essentially a point has no width. Okay, and that's why the areas are the same. So they create exactly the same area interval. The last phase of the video now, we're going to do two examples which illustrate this, and again this is using z, the standard normal variable, and hopefully we can look at the different features. Now it's important to justify, even though the calculator is going to do the grunt work, it's important to justify it and to demonstrate your understanding, and also for the sake of good communication. Okay, it's easy to teach someone how to just punch keys in the calculator, but we want to look at how much somebody knows about this too. So we have here the probability that a variable lies between -2 and 2. So we just do a quick sketch. It's up to you whether you want to draw the y-axis in or the vertical axis. You don't have to. If you want to, you can do. It's down there at -infinity. Okay, and basically in the middle we have 0 because it's a standard normal. So that's where mu is. Alright, and basically we've got this sort of shape. The shape will be the same for all these questions. It's only a sketch. Okay, so we're looking at -2 to 2. Now, by the way, when you're getting out to -3 and 3, that's an extremely broad, that's nearly 100% probability. That's nearly everything. So that gives you a bit of an idea. -2 to 2 is fairly broad. So you'd probably sketch it something a bit like this. So there's -2 and there's 2 there. It's only a sketch. Okay, so, and then of course we've got an area as such, and we just put that in there. So if you've got something like 2, that's significantly out from the center there. So that is going to be pretty big, because like with probability distributions, probability density functions, everything under the curve would have an area of 1. The total area is 1. So this will have a fairly high, fairly large answer. Now what would be nice to do would be to basically put in the keystrokes of what you're doing here. So let's have a look on the calculator first. Now again, apologies for not having my emulator software working, but hopefully this will do the job. So you've got your calculator, and probably just going to calculate, and then basically you can, the quick way of going is going menu. So what comes up on the screen, so I've hit menu, and then we need to go to option 5, probability. You could do it with stats, but probability is better, and then distributions 5 again. And what we want is normal, because we're doing normal distribution, normal CDF. Okay, so we're looking at the basically the cumulative frequency, cumulative function, sorry, and we select 2 there. And basically, we've got to look at our limits. Let's go back and see what we should put in here. So we have -2 and 2 are our limits. Now, like we said before, it doesn't matter which inequality we have here, okay, as in whether it's less than or equal to. The direction matters, but in terms of it being equal or not, it's the same as we just mentioned above there. Okay, so we put in the lower limit of -2 and the upper limit of 2. It's much easier with the modern calculators than it was back when we were using tables and older calculators like the TI-84. We simply put in -2 where it says lower bound, so enter that. We tab down, and the upper boundary was 2. We tab down. Now this is a standard normal, so the default settings will suit us there. Mu, or the mean, is 0 and the standard deviation is 1, and we hit OK, and we hit OK. That's better, and we get 0.9545. Alright, so justification there, normal CDF, put your parameters in, and 0.9545 was the probability, and there you go. So you can see we've got the statement written down, we've got the justified diagram shaded, we've got the calculator instructions, and then we've got the answer. You need to have all of those things. Final example, probability that Z, the standard normal, is above 1.734. Alright, so we put in our normal curve, and above, now 1.7 is somewhat above 0. It's only a sketch, so there we go, 1.734. Alright, and we are after the zone above that, so that's up to infinity there, and it stops at 1.7. Now hopefully you know from your work on discrete probability distributions, binomial ones in particular, that the cumulative function, the CDF, works from the bottom upwards. Now what we haven't got from the bottom upwards. Okay, so a couple of things you could do. You could use symmetry, or you could do the following. And when I say from the bottom, this cumulative starts at 0 for these distributions. Now if we do the following, if we look at from 0 to out to infinity, that is half of one whole, because the whole thing's one whole. It's symmetrical, being a standard normal distribution, so that would be 0.5. So we can break it down. So I've broken it down like this. So as I said, greater than 0, the yellow region, that has a probability of half of the whole thing, which is half of 1, which is 0.5. Now this bit here can be achieved by using your graphics calculator, so that'll be normal CDF going from 0 to 1.734 with the standard 0 and 1 for mu and sigma. And we go and achieve that then. So same menu 552 and then lower boundary 0 and 1.734, whoops, 1.734, and we've got our mu as 0, sigma is 1 for standard normal. And we've got 0.4585. So we'll round that to 4 decimal places, 0.4585. Okay, we've written that in there. And then we will simply have got to go 0.5, take that away. So 0.5, take away the previous answer. And we get 0.04146, actually to 4 decimal places, 0.0415. So there's the standard normal distribution and a couple of examples. The next video will look at when mu doesn't equal 0 and sigma doesn't equal 1, so other types of normal distributions that aren't standard normal.